Now in inverse trigonometric functions, there will be many questions on summation of series, and in summation of series, we'll be given a series in terms of inverse trigonometric function, and we need to simplify it using method of difference, which we study in sequence and series. Now say for example, this question, which is tan inverse 1 upon 1 plus 2 plus tan inverse 1 upon 1 plus 2 into 3, and it goes all the way up to tan inverse 1 upon 1 plus n into n plus 1, and say it is tan inverse of theta. Then we need to find the value of theta. Now generally what we do in these questions is we write general term for this series. Now general term for this series is TR, and it'll be tan inverse 1 upon 1 plus R into R plus 1. Now in method of difference, our objective is to express this TR as some AR minus BR in such a way that in successive terms, expression should cancel out. So we have to introduce a minus sign here, and we know that in case of tan inverse x minus y upon 1 plus xy is tan inverse x minus tan inverse y. So if we can express this tan inverse in the form x minus y upon 1 plus xy, then this problem will be simple for us. Now for this question, we can actually write this TR as tan inverse, and we can write this one as R plus 1 minus R upon 1 plus R into R plus 1. So this is tan inverse x minus y upon 1 plus xy, which we can write as tan inverse R plus 1 minus tan inverse of R. Now we need to find sum of n terms, which is T1 plus T2 plus Tn, or we can write this as summation R varies from 1 to n summation TR. Now if we write T1 in this case will be tan inverse 2 minus tan inverse 1. Second term will be, if we'll put R as 2, we'll get tan inverse 3 minus tan inverse 2. Third term will be tan inverse 4 minus tan inverse 3, and then nth term will be tan inverse n plus 1 minus tan inverse n. Now we have to add them all up to find this Sn. Now we'll add them all up. Here tan inverse 2 will cancel, tan inverse 3 will cancel. These terms they'll cancel, and we'll end up getting tan inverse n plus 1 minus tan inverse of 1, which again we can write as tan inverse n plus 1 minus 1 upon 1 plus n plus 1, and it is tan inverse n upon n plus 2. Now this S is tan inverse theta, so we can write tan inverse of theta equals tan inverse n upon n plus 2. So value of theta will be n upon n plus 2, and that's your option C. Now the next question is, if A1, A2, A3, An are in AP with common difference D, then prove that tan of tan inverse D upon 1 plus A1, A2 plus tan inverse D upon 1 plus A2, A3 plus tan inverse D upon 1 plus An minus 1 plus An is equal to n minus 1 D upon 1 plus A1, An. Now what we'll do is, we'll take this as some series S, and we'll express this as this summation tan inverse D upon 1 plus AR into AR plus 1, where the value of R varies from 1 to n minus 1. So this is our general term TR. So we can write TR as tan inverse. Now common difference is difference between any two successive terms. So we can write this as AR plus 1 minus AR upon 1 plus AR into AR plus 1, which is tan inverse AR plus 1 minus tan inverse AR. Now we'll write T1. T1 is tan inverse A2 minus tan inverse A1. T2 will be tan inverse A3 minus tan inverse A2, and Tn minus 1 will be tan inverse An minus tan inverse An minus 1. Now here these terms they'll cancel, so we'll get this sum as tan inverse An minus tan inverse of A1, which is tan inverse of An minus A1 upon 1 plus An into A1. Now we'll take this tan inverse here. So we'll get this tan s, and tan s will be an minus a1 upon 1 plus an into a1. Now an is nth term. So it will be a1 plus n minus 1d minus a1 upon 1 plus a1 into an. Now here a1 will cancel. So we have this tan s and it will be equal to n minus 1d upon 1 plus a1 into an. And this is what we need to prove. Now let us take another question, and it is cot of this summation n varies from 1 to 23 cot inverse 1 plus, and then this summation k varies from 1 to n 2k. Now first we'll simplify this summation. Now we can write this as cot of, and then this summation n varies from 1 to 23 cot inverse 1 plus, we'll take this 2 common, and then summation k. Now summation k is nothing but n plus 1 by 2. So we'll cancel this 2 with 2. So we can write this as cot of summation n varies from 1 to 23 cot inverse of 1 plus n into n plus 1. Now since n is a positive number, we can write cot inverse x as tan inverse 1 by x. So we'll actually write this as cot of, and this summation n varies from 1 to 23 tan inverse 1 upon 1 plus n into n plus 1. Now we have to express it as tan inverse x minus tan inverse y. So what we'll do is we'll actually write this as cot of, then this summation n varies from 1 to 23 tan inverse n plus 1 minus n upon 1 plus n into n plus 1. So it will be nothing but tan inverse x minus y upon 1 plus xy. So we'll write this as cot of, and then this summation n varies from 1 to 23 tan inverse n plus 1 minus tan inverse of n. Now we'll start expanding this summation. So we can write this as cot of, now we'll put n as 1, we'll get tan inverse 2 minus tan inverse 1. For n equals 2, it'll be tan inverse 3 minus tan inverse 2, and it'll continue up to 23, where it will be tan inverse 24 minus tan inverse 23. Now here these terms, they'll cancel out, and then in the end we'll get cot of tan inverse 24 minus tan inverse of 1, which we can write as cot of, now tan inverse x minus y, so it'll be 24 minus 1 upon 1 plus 24, so there'll be 25. Now tan inverse x is cot inverse 1 by x, so we can write this as cot of cot inverse 25 by 23. Now here cot and cot inverse will cancel, so answer to this expression will be simply 25 by 23, and that's your option B. Now let us take another problem, and it is we need to find sum of this infinite series, which is tan inverse 1 by 3 plus tan inverse 2 by 9 plus tan inverse 4 by 33, and this series, it continues up to infinite. Now an important step in solving such questions is to figure out its general term, or the pattern in its general term. Now we look at this first one. We know that we have to express it as tan inverse x minus y upon 1 plus xy. So we can write this 3 as 1 plus 1 into 2, and the numerator we can write this as 2 minus 1. Then for the second term we can write this as 1 plus 8, which is 2 into 4, and we can write this as 4 minus 2. And then it'll be tan inverse 1 plus 32. 32 is 4 into 8, and we can write this as 8 minus 4. And this series, it continues up to infinite. So we can write this series as tan inverse 2 minus tan inverse 1 plus tan inverse 4 minus tan inverse 2, tan inverse 8 minus tan inverse 4, and this series will continue up to infinite. Now we look at the pattern, then tan inverse 2 will cancel, tan inverse 4 will cancel. So all these successive terms, they'll cancel. Then loosely speaking, we can write this as tan inverse infinite minus tan inverse 1. The proper way of solving this question is to first write its partial sum and then take limit n tends to infinite. But here I have taken a shortcut. So I have directly expressed it as tan inverse infinite minus tan inverse 1, which is pi by 2 minus pi by 4, and it is pi by 4, and that's your option A. Now another question is, we need to find sum of this infinite series, which is cot inverse 2 plus cot inverse 8 plus cot inverse 18 plus cot inverse 32. Now we look at this series. We can actually write this series as 2 into 1 square plus cot inverse of 2 into 2 square plus cot inverse of 2 into 3 square, and this series, it continues up to infinite. Now we'll write general term for this series. General term for this series will be cot inverse 2r square. Now we can write cot inverse as tan inverse 1 upon 2r square. Now we need to simplify this, and we have to express it as tan inverse x minus tan inverse y. So what we'll do is we'll multiply by 2 and we'll divide by 2. So we'll write tan inverse 2 upon 4r square, and then we'll add 1 and subtract 1. So we can write this as tan inverse 2 upon 1 plus 2r plus 1 into 2r minus 1. So its general term will be tan inverse 2r plus 1 minus 2r minus 1 upon 1 plus 2r plus 1 into 2r minus 1. Now this is tan inverse x minus y upon 1 plus xy. So it will be tan inverse 2r plus 1 minus tan inverse 2r minus 1. Now here the first term will be tan inverse 3 minus tan inverse 1. Second term will be tan inverse 5 minus tan inverse 3. Tan inverse 7 minus tan inverse 5. And nth term is tan inverse 2n plus 1 minus tan inverse 2n minus 1. Now we'll add them all up. We'll get our partial sum. So these terms, they'll cancel. We'll get sum of n terms as tan inverse 2n plus 1 minus tan inverse of 1. Now we need to find sum of infinite terms. So we'll take this limit. So we'll take limit n tends to infinite Sn, and it'll be this limit n tends to infinite tan inverse 2n plus 1 minus tan inverse 1. Now this is tan inverse infinite, which is pi by 2, and then tan inverse 1 is pi by 4. So this value is pi by 2 minus pi by 4, which is nothing but pi by 4. So answer to this question is pi by 4, and that's your option B. Now here the question is, we need to find the sum of infinite terms of the series cot inverse 1 square plus 3 by 4 plus cot inverse 2 square plus 3 by 4, cot inverse 3 square plus 3 by 4. So we'll write this series in terms of summation, and we'll write partial sum. So we'll write summation r varies from 1 to n, and it'll be cot inverse r square plus 3 by 4, and that's your general term. So we'll write this general term as tan inverse 1 upon r square plus 3 by 4. Now what we'll do is we'll add 1 and subtract 1. So we can write this as tan inverse 1 upon 1 plus r square minus, now 3 by 4 minus 1 is 1 by 4. So we'll write this as tan inverse 1 upon 1 plus r plus 1 by 2 into r minus 1 by 2. So we can express this as tan inverse r plus 1 by 2 minus r minus 1 by 2 upon 1 plus r plus 1 by 2 into r minus 1 by 2. So its general term will be tan inverse 2r plus 1 by 2 minus tan inverse 2r minus 1 by 2. Now we'll find its partial sum. So we'll write S1. S1 will be tan inverse 3 by 2 minus tan inverse 1 by 2. S2 will be tan inverse 5 by 2 minus tan inverse 3 by 2, and then Sn will be tan inverse 2n plus 1 by 2 minus tan inverse 2n minus 1 by 2. Now here these terms they'll cancel. We'll get partial sum as tan inverse 2n plus 1 by 2 minus tan inverse 1 by 2. Now we'll take this limit n tends to infinite. Sn, it will be this tan inverse infinite, which is pi by 2. So it will be pi by 2 minus tan inverse 1 by 2, and pi by 2 minus tan inverse x is cot inverse. So it will be cot inverse 1 by 2. So answer to this question is cot inverse 1 by 2, or we can also write it as tan inverse 2. And that's your option B. Now here the question is, we'll need to find sum of infinite terms of the series cot inverse 2 square plus 1 by 2 plus cot inverse 2 cube plus 1 upon 2 square, and the series it continues up to infinite. We'll write its partial sum Sn, and there'll be this summation cot inverse 2 to the power r plus 1 upon 2 to the power r, where r varies from 1 to n. And now this is our general term. So we can write TRS, and we'll change it in terms of tan inverse. So we'll write tan inverse 1 upon 2 to the power of r plus 1 plus 1 upon 2 to the power of r. So we can write TRS tan inverse 2 to the power of r upon 1 plus 2 to the power r into 2 to the power of r plus 1. Now in the numerator, we can write this as 2 to the power of r plus 1 minus 2 to the power of r upon 1 plus 2 to the power of r plus 1 into 2 to the power of r. So it will be tan inverse 2 to the power of r plus 1 minus tan inverse of 2 to the power r. Now we'll find its partial sum. T1, it will be tan inverse 2 square minus tan inverse 2. T2 will be tan inverse 2 cube minus tan inverse 2 square, and then Tn will be tan inverse 2 to the power of n plus 1 minus tan inverse of 2 to the power n. Now here successive terms they'll cancel. So its partial sum will be tan inverse 2 to the power of n plus 1 minus tan inverse of 2. Now we'll take limit n tends to infinite Sn. Now this is tan inverse infinite, so it will be pi by 2 minus tan inverse 2, and it is nothing but cot inverse of 2. So answer to this series is cot inverse of 2. Now here the question is, we'll need to find sum of this series, which is summation r varies from 1 to n sin inverse under root r minus 1 upon under root r plus 1. So our general term is sin inverse under root r minus under root r minus 1 upon under root r plus 1. Now one of the way of solving this question is to change it in terms of tan. So we'll take this as theta, then sin theta will be under root r minus 1, and here it will be r into r plus 1. We have to find this base. So this base, say b, it will be b square equals under root of r into r plus 1 square minus under root of r minus 1 square. So this b square will be r into r plus 1 minus, and here will be r plus r minus 1 minus 2 times under root of r into r minus 1. Now we'll simplify this. We'll get b square as r square plus r minus 2r plus 1 minus 2 into under root of r into r minus 1. Here r and minus 2r will cancel, so we'll get r square minus r plus 1 minus 2 r minus 1. So it will be actually under root of r minus 1 whole square plus 1 minus 2 under root of r into r minus 1. So we can write this b square as 1 plus under root of r into r minus 1 whole square. So this b is actually 1 plus under root of r into r minus 1. So we can express this sine inverse as tan inverse under root of r minus 1 upon 1 plus under root of r into r minus 1, which is nothing but tan inverse x minus y upon 1 plus xy. So we can express it as tan inverse under root r minus tan inverse under root r minus 1. Now we need to find its partial sum Sn. So we'll write T1. T1 will be tan inverse under root 1 minus tan inverse 0. T2 will be tan inverse root 2 minus tan inverse under root 1. T3 will be tan inverse root 3 minus tan inverse root 2, and then Tn will be tan inverse under root n minus tan inverse of under root n minus 1. Now if we'll add them all up, tan inverse 1 will cancel, tan inverse 2 will cancel. We'll get this result Sn as tan inverse of under root n, and that's your option 3. Now here again we are given some series secant inverse root 2 secant inverse under root 10 by 3, and it goes all the way up to secant inverse under root of n square plus 1 into n square minus 2n plus 2 upon n square minus n plus 1 whole square. And the answer they have given in terms of tan inverse. So here also we have to change the series in terms of tan inverse. Now we'll write its general term, then its rth term is secant inverse under root of r square plus 1 into r square minus 2r plus 2 upon r square minus r plus 1 whole square. Now we'll take this as theta, then secant theta is under root of r square plus 1 into r square minus 2r plus 2, and here it will be r square minus r plus 1. Now we have to find its perpendicular. Now p square will be r square plus 1 into r square minus 2r plus 2, and then minus r square minus r plus 1 whole square. So we'll write this as r to the power 4 minus 2r cube plus 2r square plus r square minus 2r plus 2, and then minus r to the power 4 plus r square plus 1 minus 2r cube plus 2r square minus 2r. Now here r to the power 4 will cancel, 2r cube will also cancel, and 2r square will also cancel, and minus 2r will also cancel, r square will also cancel. So value of p is simply 1. So this is 1. So we can write its general term tr as tan inverse 1 upon 1 plus r into r minus 1, which is tan inverse r minus 1 upon 1 plus r into r minus 1. So its rth term will be tan inverse r minus tan inverse r minus 1. Now you'll find its partial sum. T1, it is tan inverse 1 minus tan inverse 0. T2 is tan inverse 2 minus tan inverse 1. And Tn is tan inverse n minus tan inverse n minus 1. Now we'll add them all up. Tan inverse 1 will cancel. These terms, they'll cancel. So we'll get our partial sum and it'll be simply tan inverse of n, and that's your option B. Now here the problem is, we need to find the value of cosec inverse root 5, cosec inverse root 65, cosec inverse root 325, and it goes all the way up to infinite. Now what we'll do is, we'll change each of this expression in terms of tan inverse. Now cosec theta is root 5. So this is theta, this is root 5, this is 1, and here this value will be 2. So we'll write this as tan inverse 1 by 2. Now for the second one, we'll have root 65. This is 1 and it'll be root 64. It'll be 8. So it'll be tan inverse 1 by 8. Next one it'll be 325, 1, and it'll be under root of 324. It'll be tan inverse 1 by 18, and this series will continue up to infinite. Now in this form, we do not see any pattern. So actually I'll try and express it as 2 by 4 tan inverse 2 by 16 tan inverse 2 by 36, and we'll write this as 1 plus 1 into 3 tan inverse 1 plus 3 into 5 tan inverse 1 plus 5 into 7, and the series it continues up to infinite. So we can write this series as tan inverse 3 minus 1 upon 1 plus 1 into 3 tan inverse 5 minus 3 upon 1 plus 3 into 5 tan inverse 7 minus 5 upon 1 plus 5 into 7, and so on. So we'll write this as tan inverse 3 minus tan inverse 1 plus tan inverse 5 minus tan inverse 3 tan inverse 7 minus tan inverse 5. It goes all the way up to infinite. Now here 3 will cancel, 5 will cancel. So in the end, loosely speaking, we'll get tan inverse infinite minus tan inverse 1, which is pi by 2 minus pi by 4, and it is pi by 4. So value of k will be simply 1. Now let us take another problem, and it is this series S is summation r varies from 1 to 90 2r upon 2 plus r square plus r to the power 4. Now again we have to introduce a minus sign. Now here what we'll do is, we'll add r square and we'll subtract r square. So we'll write this series as the summation r varies from 1 to 90, and it'll be 2r, and here we'll take this 1 and then 1 plus 2r square plus r to the power 4 minus r square. So we can write this series as this summation r varies from 1 to 90, and it'll be 2r upon 1 plus it'll be r square plus 1 whole square minus r square. Now this is a plus b into a minus b. So we can express this as this summation r varies from 1 to 90 1 plus r square plus r plus 1 into r square minus r plus 1, and it'll be r square plus r plus 1 minus r square minus r plus 1, and we have tan inverse all the way. Now this is tan inverse x minus y upon 1 plus xy. So we can write this as this summation r varies from 1 to 90 tan inverse r square plus r plus 1 minus tan inverse r square minus r plus 1. Now we need to find this summation when r varies from 1 to 90. Suppose this is TR. Now we'll write T1, and T1 will be tan inverse 3 minus tan inverse 1. T2, it will be tan inverse 7 minus tan inverse 3. T3 will be tan inverse 13 minus tan inverse 7, and it'll continue up to T90, which is tan inverse 90 square plus 90 plus 1 minus tan inverse 90 square minus 90 plus 1. Now we'll add them all up, we'll get our Sn. Now here tan inverse 3 will cancel. So in the end, we'll get this sum S90 as tan inverse 8100 plus 90 plus 1 minus tan inverse 1, which is tan inverse 8191 minus tan inverse 1, and it'll be tan inverse 8190 upon 8192. Now we'll take this 10 here, so we'll write 10s equals 8190 upon 8192. Now we need to find the value of 8190 cot s, and it'll be simply 8192. So answer to this question will be 8192, and that is the answer to this question. Now the next question is very standard question. We can write this s and x as this summation tan inverse k plus 1x minus kx upon 1 plus kx into k plus 1x, which is this summation tan inverse k plus 1x minus tan inverse of kx. Now we put the value of this summation, then it starts from 1, so it will be tan inverse 2x minus tan inverse x plus tan inverse 3x minus tan inverse 2x, and finally it will go up to tan inverse n plus 1x minus tan inverse nx. Now all these, they'll cancel, so we'll get this s and x as tan inverse n plus 1x minus tan inverse of x, which is tan inverse a minus b. So it will be this nx upon 1 plus a into b. So it will be n plus 1 into x square, and that's your function s n x. Now the first part is we need to find s 10x. Now this s 10x will be tan inverse 10x upon 1 plus 11x square. Now since x is greater than 0, we can write this as cot inverse 1 plus 11x square upon 10x, and we know that cot inverse x is pi by 2 minus tan inverse x, so it will be pi by 2 minus tan inverse 1 plus 11x square upon 10x. So that means this option A, it is correct. Now if we look at this option B, then this cot of this limit n tends to infinite. Now if we take limit n tends to infinite, this limit will be tan inverse of, now coefficient of n, here it is x and here it is x square. Now this x and x will cancel, so we'll get this as cot of tan inverse of 1 by x, and since x is greater than 0, it is nothing but it is cot of cot inverse of x, which is nothing but x. So that means this option B is also correct. Now we look at this S3x. Now it says S3x equals pi by 4 has a root n 0 to infinite. Now S3 is tan inverse 3x upon 1 plus 4x square, and if we take it equal to pi by 4, then we'll get this as 4x square minus 3x plus 1 equals 0. Now for this, if we find D is 9 minus 16, which is less than 0, that means this is always positive. So this equation, it won't have any real root. So that means this option C, it is incorrect. And then finally, this D, which is 10 SNX. Now if we look at this 10 SNX, now this 10 Sn x will be nx upon 1 plus n plus 1 x square. Now if we take this as y and if we differentiate this function dy by dx, then it will be equal to 1 minus n plus 1 x square into n upon 1 plus n plus 1 x square whole square. So here we'll get 1 root and which is 1 upon under root of n plus 1. Now this is plus and this is minus. So this function, it will have a local maxima at 1 upon under root n plus 1. Now if we find its value at 1 upon under root n plus 1, this value will be n upon under root of n plus 1 by 2, which is n upon 2 under root n plus 1. Now this is greater than n upon 2 root n, which is under root n by 2. So this value is always greater than 1 by 2, not less than 1 by 2. So that means this option D is incorrect. So the correct options are A and B. In this video, we'll be discussing graphs of sin inverse of mod sin x and cos inverse of mod cos x, and we'll also discuss some questions related to it. Now, when we look at this function, which is y equals sin inverse of mod sin x, we know that this function will be periodic with period pi, because period of mod sin x is pi. So what we'll do is we'll draw the graph of sin inverse of mod sin x in 0 to pi, and then we'll repeat the graph for all other intervals. So what we'll do is we'll take our interval from minus pi by 2 to plus pi by 2. Now first case, when x lies between 0 to pi by 2. Now in 0 to pi by 2, sin x is positive, so mod sin x will be simply sin x. So we can simply write this as y equals sin inverse of sin x, and in principal value range, sin inverse of sin x is nothing but it is x. So from 0 to pi by 2, this graph is simply y equals x. Now in the second interval, when x lies between minus pi by 2 to 0, in this interval sin x is negative, so therefore we'll need to write mod sin x is minus sin x. So we'll write sin inverse of minus sin x, and sin inverse of minus x is minus sin inverse of sin x. Now x still lies in principal value range, so here it will be simply minus x. So we'll draw this graph, then from 0 to pi by 2, it is plus x, and from minus pi by 2 to 0, it is minus x. So all we need to do is we'll just need to repeat this graph to get the graph of sin inverse of mod sin x. So that is the graph of sin inverse of mod sin x, and this is pi, 2 pi, minus pi, and minus 2 pi. And we also know how to write definitions for different parts. Now for this part between pi by 2 and pi, here the definition will be minus x plus pi. Here it will be x minus pi. Here will be minus x plus 2 pi. This one is going to be x plus pi. Here it will be minus x minus pi. So this is how we can draw the graph of sin inverse of mod sin x, and we can also write definition of sin inverse of mod. Now we look at the graph of sin x and mod sin x, then from 0 to pi, both the graphs, they're same. So in 0 to pi, graph of sin inverse of sin x will be same. So another way of drawing the same graph can be from 0 to pi, draw this graph and then repeat the graph. So again, we'll end up getting the same graph. So this is how we draw the graph of sine inverse of sine x. Now we look at the graph of y equals cos inverse of mod cos x. Now again, cos inverse of mod cos x, it will have fundamental period of pi. Now we look at the graph of cos x. And mod cos x, the graph of mod cos x and cos x is same between minus pi by 2 and plus pi by 2, which is an interval of length pi. In this interval, graph of cos inverse of mod cos x will be same as graph of cos inverse of cos x. Now, if we look at the graph of cos inverse of cos x, then this graph, it will be x from 0 to pi by 2 and it will be minus x from 0 to minus pi by 2. Now again, we'll repeat the same graph. And this is the graph of y equals cos inverse of mod cos x. So as you can see, graph of sine inverse of mod sine x is same as graph of cos inverse of mod cos x, and their definitions are also same. So this is how we draw the graph of sine inverse of mod sine x and cos inverse of mod cos x. Now let us take some problems. Find the range of the function square root of mod of sine inverse of mod sine x minus cos inverse of mod cos x. Now we'll recall the graph of sine inverse of mod sine x and cos inverse of mod cos x. This is the graph for y equals sine inverse of mod sine x, and since sine inverse of sine x is greater than or equal to 0, then graph of mod of sine inverse of mod sine x will be same as graph of sine inverse of mod sine x. Now we have also studied that graph of cos inverse of cos x is same as graph of sine inverse of sine x. So we can write this function fx as square root of sine inverse of mod sine x minus cos inverse of mod cos x, and since both these functions, they have the same definition, they are same function. So this is simply 0. So this function, it is a constant function and its value is 0. So range of this function is simply 0. Now here the question is, if sine inverse mod cos x minus cos inverse mod sine x equals lambda has at least one solution, then lambda belongs to which of the following intervals? Now we can write sine inverse of mod cos x as pi by 2 minus cos inverse of mod cos x, and in the same way we can write cos inverse of mod sine x as pi by 2 minus sine inverse of mod sine x. Now we'll replace these two definitions, then we can simply write this as sine inverse of mod sine x minus cos inverse of mod cos x, and it should be lambda. Now we know that definitions of sine inverse of mod sine x and cos inverse of mod cos x, they are exactly same. So both these functions, they'll have the same value at all the points. So value of this function is simply 0. So the only possible value of lambda if this equation has a solution is 0, because this function, it is a constant function whose value is always 0. So answer to this question is this option A. Now here the question is, draw the graph of fx equals sine inverse of mod sine x plus cos inverse of cos x. Find the range of the function. Find the points of non-differentiability. Also find the value of this integral from 0 to 10 pi sine inverse of mod sine x plus cos inverse of cos x dx. Now we are given this function fx, which is sine inverse of mod sin x plus cos inverse of cos x. Now period for this function is pi and fundamental period for this second function is 2 pi. So this function fx, it is periodic with the period 2 pi. Now what we'll do is we'll write the definition of fx between 0 to 2 pi. We'll draw its graph and then we'll generalize the function. Now we'll recall the graph of sin inverse of mod sin x. We know that this graph is from 0 to pi by 2 x. From pi by 2 to pi, it is minus x plus pi. From pi to 3 pi by 2, it is x minus pi. And then from 3 pi by 2 to 2 pi, it is minus x plus 2 pi. So this is the graph of y equals sin inverse of mod sin x. Now we'll draw the graph of cos inverse of cos x. It's a very standard function. So this is 0, pi and 2 pi. Now between 0 to pi it is x, and between pi to 2 pi it is minus x plus 2 pi. Now we write definitions for this function fx. Now first definition is when x lies between 0 to pi by 2. Between 0 to pi by 2, both the definitions, they are x. So it will be simply 2x. From pi by 2 to pi, here the definition is minus x plus pi, and here it is plus x. So we'll add them, we'll get this as pi. Between pi and 3 pi by 2, definition here is x minus pi, and here the definition is minus x plus 2 pi. So we'll add them, we'll again end up getting this value as pi, and then between 3 pi by 2 and 2 pi, this is minus x plus 2 pi, and it is also minus x plus 2 pi. So it will be 4 pi minus 2x. So we can write this function fx as 2x when x lies between 0 and pi by 2. It will be pi between pi by 2 and 3 pi by 2, and then we have 4 pi minus 2x when x lies between 3 pi by 2 and 2 pi. Now we'll draw the graph of fx. We'll draw the axis. Then we'll mark the points on axis. So this is pi by 2, pi, 3 pi by 2 and 2 pi. Here also let it be pi by 2 and let it be pi. Now first is y equals 2x. When x is 0, it is 0, and when x is pi by 2, it is pi. So we'll draw this graph. Now between pi by 2 and 3 pi by 2, this value is pi. Now between 3 pi by 2 and 2 pi, if we'll put x as 3 pi by 2, we'll get this as pi. And we'll put x as 2 pi, we'll get this result as 0. So between 3 pi by 2 and 2 pi, it'll be simply this straight line. So that is the graph of this function fx, which is sin inverse of mod sin x plus cos inverse of cos x. Now this graph will repeat in the same fashion. So this is how we can draw the graph of sin inverse of mod sin x and cos inverse of cos x. Now as you can see, this function is continuous in x belongs to R, but it is not differentiable at pi by 2, 3 pi by 2, 0, 2 pi. So it is not differentiable at odd multiple of pi by 2 and at 2n pi. So it is not differentiable at x equals 2n pi and 2n plus 1 pi by 2. Now we need to find range of this function also. So range of this function is from 0 to pi. as we can see, this graph, it lies entirely in this interval from 0 to pi. So the range of this function, it is from 0 to pi. Now we need to find the value of this integral from 0 to 10 pi fx dx. Now since this function is periodic with a period 2 pi and 10 pi is a multiple of 2 pi, we can simply write this as 5 into 0 to 2 pi fx dx, and this integral from 0 to 2 pi fx dx is nothing but area under this trapezium. So we can simply write this as 5 and then 1 by 2. Now sum of lengths of parallel sides. Now this is 2 pi and this is 3 pi by 2 minus pi by 2, which is simply pi, and then this height, which is also pi. So this area, it will be 5 by 2 into 3 pi square. So it will be 15 pi square by 2. So value of this integral will be 15 pi square by 2. Now there will be questions on inequalities in inverse trigonometric function. Now here the question is, solve the inequality arc secant x square minus 6 arc secant x plus 8 is greater than 0. So let us take arc secant of x as some y. So we can write this as y square minus 6y plus 8 greater than 0. Now it will be y minus 2, y minus 4 greater than 0. So this is 2 and 4. So plus, minus and plus. So either the value of y should be less than 2 or value of y should be greater than 4. Now we'll need the condition that secant inverse of x is either less than 2 or secant inverse of x is greater than 4. Now we know that principal value range of secant inverse of x is from 0 to pi, which is less than 4. So we won't get any solution in this interval. So the only condition that we are getting in this case is secant inverse of x is less than 2. Now we'll draw the graph of secant inverse of x. Then it is 0, pi by 2 and pi. Now this is the graph of secant inverse of x. Now we want this secant inverse x value to be less than 2. So we'll draw a line at y equals to. Now this point of intersection will be secant 2. Now we need to find the interval where the graph of secant inverse of x lies below the graph of y equals 2 line. So it will be in this interval and in this interval. So answer to this inequality will be x belongs to from minus infinite to secant 2 union 1 to infinite, and that is the answer to this question. Now here the question is, solve the following inequalities. Now the first one is arc cot inverse x whole square minus 5 arc cot x plus 6 is greater than 0. So what we'll do is we'll let y equals cot inverse of x. Now we can write this as y square minus 5y plus 6 greater than 0. Now it will be y minus 2, y minus 3 greater than 0. Now this is 2 and 3. So it will be plus, minus and plus. So we'll get the condition that either the value of y is less than 2 or the value of y is greater than 3. Or cot inverse of x, it should be less than 2 or cot inverse of x should be greater than 3. Now we'll draw the graph of cot inverse of x. Its principal value ranges from 0 to pi, both not inclusive. And that is the graph of cot inverse of x. Now we'll draw a line at y equals 2 and y equals 3. So this is y equals 2 and this is y equals 3. Now this is cot inverse x equals 3. So it will be cot 3 and this value it will be simply cot 2. Now we need the portion of graph which is either below this y equals 2 line, which is this region, or which is above y equals 3 line, which is this region. So solution to this inequality will be the value of x should lie between minus infinite to cot 3 union cot 2 to infinite. Now the second question is, solve this inequality. Sin inverse of x is greater than cos inverse of x. So we'll draw both the graphs. Now this is the graph of sin inverse of x. Now this is minus 1 and this is plus 1. This is pi by 2 and it is minus pi by 2. Now we'll draw the graph of cos inverse of x. It'll be pi at minus 1 and then at 0 it'll be pi by 2 and at 1 it'll be simply 0. So first we'll need to find this point of intersection where sin inverse of x is equal to cos inverse of x, and we know that they'll be equal when they are both pi by 4 and the value is 1 by root 2. Now we'll need to find the region where sin inverse of x is greater than cos inverse of x. So we'll need to find the region where graph of sin inverse of x lies above the graph of cos inverse of x, and it lies in this interval. So answer to this question will be x belongs to 1 by root 2 to 1. Now the third one is tan square of sin inverse of x and it is greater than 1. Now we'll take sin inverse of x as theta. We'll get sin theta equals x. Now this is theta, this is x, this is 1, and it'll be under root of 1 minus x square. Now tan theta here will be x upon under root of 1 minus x square. So we'll write x upon under root of 1 minus x square whole square, and it should be greater than 1, which is x square upon 1 minus x square, it is greater than 1. So we'll write x square upon 1 minus x square minus 1, it should be greater than 0. So we'll get x square minus 1 plus x square upon 1 minus x square, it should be greater than 0, which is 2x square minus 1 upon 1 minus x square, it is greater than 0. Now here the critical values are plus minus 1 by root 2 and plus or minus 1. Now we'll plot these values on a number line. So we'll get 1 by root 2 and then 1. Here it will be minus 1 by root 2 and then minus 1. Rightmost is minus. So this is minus, plus, minus, plus and minus. We need greater than 0. So it will be x belongs to minus 1 to minus 1 by root 2 union 1 by root 2 to 1, and that is the answer to this question. Now here the question is solve for x, and it is given as sin inverse of sine, and it is 2x square plus 4 upon 1 plus x square, and it is less than pi minus 3. Now if we look at 2x square plus 4 upon 1 plus x square, we can write this as 2x square plus 1 plus 2 upon 1 plus x square, which is 2 plus 2 upon 1 plus x square. Now we know that 1 plus x square, it lies between 1 and infinite, and if we take reciprocal, 1 upon 1 plus x square will lie between 0 and 1. Now we'll multiply it with 2, we'll get 0, 2 upon 1 plus x square, and it'll be less than or equal to 2, and we'll add 2, then we can simply write 2x square plus 4 upon 1 plus x square, it'll be greater than 2 but less than or equal to 4. Now we'll need to find definition of sine inverse of sine x when x lies between 2 and 4. Now we'll draw the graph of sine inverse of sine x. This graph will be x from minus pi by 2 to plus pi by 2. Then it'll be this function. And then it'll go like this. So this is pi by 2 and it is 3 pi by 2. Now 2 will be greater than pi by 2 and 4 will be less than 3 pi by 2. So within this interval, when x lies between 2 and 4, the definition of this function will be minus x plus pi. So we can write this sine inverse of sine 2x square plus 4 upon 1 plus x square as pi minus 2x square plus 4 upon 1 plus x square, and it should be less than pi minus 3. Now we'll cancel this pi with pi. We can write 3 minus 2x square plus 4 upon 1 plus x square. It should be less than 0. So it will be 3 plus 3x square minus 2x square minus 4 upon 1 plus x square, and it will be less than 0. So we'll get x square minus 1 upon x square plus 1. It should be less than 0. Now x square plus 1, it is positive. So we can cancel it. So we'll get x square minus 1 is less than 0. That is mod x is less than 1. That is x lies between minus 1 and plus 1. And that is the answer to this question. Now here the question is the least integral value of k for which this inequality is true for all x belongs to R. Now here first we need to find the value of sine inverse of sine 12 and cos inverse of cos 12. Now we'll draw the graph of sine inverse of sine x. So this is pi, 2 pi, 3 pi and 4 pi. Now 12 will lie somewhere here. Now this definition is x minus 4 pi. So sine inverse of sine 12 will be simply 12 minus 4 pi. Now we'll draw the graph of cos inverse of cos x. So this is 0, pi, 2 pi, 3 pi and 4 pi. Now 12 will lie here. Now this definition is minus x plus 4 pi. So cos inverse of cos 12 will be minus 12 plus 4 pi. Now we'll add them. Everything will cancel. So this is nothing but 0. So this right hand side is nothing but 0. So we get our question that we need to find least integral value of k for which k minus 2x square plus 8x plus k plus 4, it is greater than 0 for all x belongs to R. Now it is a quadratic expression. A quadratic expression is always positive when a is greater than 0 and d is less than 0. Now if we look at a is greater than 0, then the condition is k minus 2 is greater than 0 and value of k is greater than 2, and the second condition that the value of d is less than 0. Now d in this case is 64 minus 4 k minus 2 k plus 4, it is less than 0. Now we'll divide it by 4. So it will be 16 minus k square plus 2k minus 8 will be less than 0, or we can write this as k square plus 2k minus 8 minus 16, it is greater than 0, which is k square plus 2k minus 24 is greater than 0. Now we'll write this as k plus 6 k minus 4 will be greater than 0. So this is minus 6 and this is 4 plus minus and plus. Here the value of k is either greater than 4 or the value of k is greater than 6. But we already know that k is greater than 2. So the condition that we'll get from here is value of k should be greater than 4. Now the least integral value of k for which this inequality always holds is k equals 5, and that's your option D. Now this is one interesting question in inequalities, and it says if T1 is sine inverse x to the power sine inverse x, T2 is sin inverse x to the power cos inverse x, T3 is cos inverse x to the power sin inverse x, and T4 is cos inverse x to the power cos inverse x. Then in the following intervals, which of the following option matches? Now what we'll do is, we'll draw the graph of sin inverse of x and we'll also draw the graph of cos inverse of x. So let us draw the axis. This is -1 and this is +1. This is pi by 2 and this is say pi, and this is minus pi by 2. Now we'll draw the graph of sin inverse of x. So that's the graph of sin inverse of x, and we'll draw the graph of cos inverse of x. So the graph in red is cos inverse of x and the graph in blue is sin inverse of x, and both these graphs, they'll intersect at 1 by root 2, and here this value, it will be pi by 4. Now pi by 4 is 0.8 something and pi by 2 is 1.54. If we draw a line at y equals 1, so this is cos 1 and this value here, it will be sin 1. Now first we'll begin with this interval, which is when x belongs to 0 to cos 1. So if x belongs to 0 to cos 1, which is this interval, cos inverse x is greater than 1 and sin inverse of x is less than 1. So when cos inverse of x is greater than 1 and sin inverse of x is less than 1, the maximum of all these four expressions will be cos inverse x to the power cos inverse x, and then it will be greater than cos inverse x to the power sin inverse x, because this again will be greater than 1. Now we have to look for power of sin inverse x. Now sin inverse x lies between 0 and 1. And as the power increases, the value decreases. So that means the next one should be sin inverse x to the power sin inverse of x, and finally the last one will be sin inverse of x to the power cos inverse of x. So cos inverse of cos x is T4. So T4, it will be greater than T3. It will be greater than T1 and it will be greater than T2. So this A, it matches with T4, T3, T1 and T2, which is Q. So A matches with Q. Now we'll take this second interval when x lies between cos 1 and 1 by root 2. So between cos 1 and 1 by root 2, both these values, cos inverse and sin inverse, they lie between 0 and 1. Now the value of cos inverse will lie between pi by 4 and 1, and value of sin inverse will lie between 0 and pi by 4. So here cos inverse x is greater than sin inverse of x. So for this part B, that is when x lies between cos 1 and 1 by root 2, cos inverse of x is greater than sin inverse of x, but both these values, they lie between 0 and 1. Now since cos inverse x is greater than sin inverse x, so if we have same power, then power of cos inverse x will be greater than power of sin inverse of x. Now between cos inverse x to the power cos inverse x and cos inverse x to the power sin inverse x, as the number lies between 0 and 1, as the power increases, the value decreases. So here the highest value will be cos inverse x to the power sin inverse x, and it will be greater than cos inverse x to the power cos inverse of x. Now we have sin inverse x to the power sin inverse x and cos inverse x. Now again sin inverse x is less than cos inverse of x, so we'll write sine inverse x to the power sine inverse of x will be greater than sine inverse x to the power cos inverse of x. So here in this case, cos inverse of sine x, it is t3. It is greater than cos inverse of cos x, t4, sine inverse of sine x, t1, and sine inverse of cos x, t2. So the condition here will be t3 is greater than t4 is greater than t1 is greater than t2. So this B, it matches with S. Now we'll come to this third case when x lies between 1 by root 2 and sine 1. Now in between 1 by root 2 and sine 1, both these values, sine inverse and cos inverse, they lie between 0 and 1. But here, sine inverse x, it is greater than cos inverse of x, and both these values, they lie between 0 and 1. Now here, since sine inverse x is greater than cos inverse x, so sine inverse x to the power cos inverse x will be greater than sine inverse x to the power sine inverse x, and cos inverse x to the power cos inverse x will be greater than cos inverse x to the power sine inverse of x. Now sine inverse x to the power cos inverse x, it is t2. So t2, it will be greater than t1, it will be greater than t4, and it will be greater than t3. So t2 is greater than t1, is greater than t4, is greater than t3. Now this option P and R, they are same. So this R has to be T2 and T1. So this C, it matches with R. And finally, sine inverse x is greater than 1 and cos inverse x is less than 1. So in this case, sine inverse x to the power sine inverse of x will be greater than sine inverse of x to the power cos inverse of x, and will be greater than cos inverse x to the power cos inverse x, and it is greater than cos inverse x to the power sine inverse of x. Now sine inverse of sine x, it is t1. So t1 is greater than t2, is greater than t4, and it is greater than t3. So this option D, it matches with P. So A matches with Q, B matches with S, C matches with R, and D, it matches with P, and that is the answer to this question, QSRP.